Hello and welcome everyone. My name is Seva, and today I will be talking about coroutines. I'll tell you what has been changed in coroutines since the last major update, how the programming model with coroutines has been changed, and what to expect in the future versions of Kotlin X coroutines. But first, let's talk about debugging. Coroutines debugging was one of our known major and long-standing pain points known to any developer who tried to debug an application with coroutines in it. And this experience, it was far from perfect. Stack traces were incomplete, local variables were missing, and suspended coroutines were almost impossible to find. Well, I'm happy to tell you that it has been changed. But first, let's take a look at this example. It's a simple function, it has a busy loop in it, it receives elements from a channel, processes them, nothing too fancy. Suppose you have a bug somewhere here. What are you going to do about it? Well, probably you'll write some kind of unit test or sample application, you'll put a breakpoint, you'll start it, you'll wait for breakpoint to hit, and you'll start examining your program state. What shall you see in the debugger? Previously, you would see something like this. Our latest stack frame, which is our process user events, its local variables, its arguments, and that's it. You won't be able to see, let's say, who called this function, or what local variables or arguments call ahead. And it's not because the stack trace is broken. No, it's a real stack trace. And it is because how coroutines are implemented internally. But still, it's not what you want to see, because it's not that useful. But if you have a recent enough IntelliJ IDEA version, which is 2020.1, you'll see a completely different picture. You'll see a proper stack trace here. But what has been changed? Your program, it stays the same. Execution of your program, Kotlin compiler versions, and so on, they all remain the same. It's actually IDEA who became smarter. Now it's able to detect that the current thread is executing a coroutine, it recovers its stack trace, and it draws it here. The stack trace, it isn't real. For example, a tool like JStack, it won't show you here. It won't show you it. But still, it's what you want to see. And even though this stack trace isn't real, it behaves like a real one. You can, let's say, examine stack frames, you can see its local variables, its arguments, you can execute statements over them, you can put watches, you can change them. Basically, you can do anything you would like to do with a regular debugging. Even better, if you have a recent enough Kotlin X coroutines version in the class path, you'll see an additional coroutine stub window, which is pretty similar to threads stub in regular IntelliJ IDEA debugging. This tab, it shows you all the coroutines your application has, including running coroutines, suspended coroutines, and even created but not yet started. And like with threads, you can observe them, you can see where they blocked, suspended, running, what are the local variables, and so on. Even better, if you got lost and have no idea where some particular coroutine came from, you can see a coroutine creation stack trace here, which will help you to detect where this particular coroutine came from. Finally, IntelliJ IDEA and Debugger have first-class support of coroutines. And with these changes, we expect coroutines debugging be as simple and as pleasant as regular debugging. So have a nice debugging, but enough of it. Let's talk about flow. But before telling you what has been changed in the flow, let me remind what flow is. Basically, flow is a sequence. And like all the Kotlin sequences, it can be built, it can be transformed, and can be mapped, filtered, or consumed. Or in flow terms, they can be collected. But what's the main difference between Kotlin sequences and flows? And this difference is suspension. In flow, you can suspend everywhere. You can suspend in builder function, you can suspend in maps, transforms, filters, you can even suspend in terminal operators. And this suspension, it actually behaves like a back pressure management, but you don't have to do anything about it. Compiler will handle it by itself. Shortly speaking, flow is as simple as Kotlin sequences, but it also has all the benefits of reactive programming, where you don't have to manage back pressure. Our recent addition to flow is state flow. But before telling you what state flow is, let's talk a bit about the problem domain. What state is, what problems can be modeled with state, and how to manage it. According to Oxford Dictionary, state is a condition or way of being that exists at a particular point of time. A good enough example of state is a plain old variable. And this variable, it has a lot of values during its lifetime, but at any particular point of time, it has one, and you're interested only in its latest value. A bit more complex example will be a downloading state. It has a straightforward state transition from not initialized to started to being at some point of progress, and finally a successful download or failed one. And you're not interested in any intermediate results here as well. If you have completed download, you're not interested in receiving events of being at each particular point of progress. You're interested in whether this download is completed or not. So how can we manage it? And how can we manage it in a reactive and responsive manner, ideally as a flow? Previously, we would recommend to use conflated broadcast channel. But conflated broadcast channel is a channel, and channels are complicated beasts. They, let's say, have a determined life cycle and a lot of API, and thus they're a bit slow. It's not like all channels are slow, no. But this particular problem, state management, can be solved in a much more elegant and concise manner. Even more, channels have a lot of API. For example, they can be closed, or they can be canceled. And it's not really a good fit for state management because you cannot close a variable. You cannot cancel the state. So instead, we decided to deprecate conflated broadcast channel and introduce our own new solution, state flow. State flow is just a flow with a value, with its state. And with the best additions of Kotlin standard library, it comes in two flavors, read-only state flow and mutable state flow, which has its state mutable. So you are free to decide what to expose to your clients and what to use internally in your implementation. And any update to this value, to its state, will be reflected in all flow collectors by emitting a value with state update. So how can we manage our downloading state with state flow? Let's take a look at the example. First, we have to initialize the flow. And for that, we have a mutable state flow factory. And take a note here. We create and use a mutable state flow internally, but for our clients, we expose a read-only flow, so they won't be able to mutate it. And we have a downloading function. In it, we initialize the state with initial value, we create a connection, and start our heavy lifting. When new data arrive, we start processing it, and we update our state with a progress, or with some kind of percent. And eventually, we'll update it with its final value, successful download. And that's it. You don't have any channels here, you don't have any coroutines here, or any brand new concept to learn. It's just as simple as that. You have a plain old variable as the implementation detail, and for your clients, you expose a simple and familiar flow. But what if, instead of managing a state, you want to manage a series of state updates, or generally speaking, an event stream? For that, we have a shared flow. But again, let's talk about problem first, about its domain, what's a real-world example, and only then let's discuss a solution. A good example of event stream will be a CO2 detector device. And CO2 detector device is a source of events, and its measurements, a level of CO2 in your apartment, is events. And here, you are not interested in each particular event. You're interested in a few latest ones. For example, to calculate a windowed average or smooth down the spikes. And this is a hardware device. It's real. You have to connect to it. And this connection is typically costly, so you don't want to duplicate it for each listener. You want to share it. Let's further discuss general constraints of event processing systems. First of all, it's a costly connection. Even connecting to a simple device as CO2 detector may take up to a few seconds, so you don't want to pay this price each time you want to receive some data from it. So you want to share this connection. Secondly, it's laziness. User may want to close the page before the source had a chance to initialize, or the whole coroutine scope can be canceled. And you don't want to create the connection when it's not really necessary, so it should be lazy. Or, in third terms, it should be cold. Thirdly, clients are typically interested in a few latest values, and they're not ready to wait for new ones, because they may not arrive soon, or they may never arrive because, let's say, a device got stuck somewhere in a hardware problem. And take a note here, this is not something channels are capable of, so we cannot model and solve this problem with channels, at least easily. Finally, a significant degree of flexibility is required to manage the source of events. Because it is a connection, it is a resource. So you want to close it, but when to close it? Some clients may want to close it as soon as there is no listeners. Others may want to wait for a few seconds to avoid paying reinitialization costs if new clients will arrive soon. And in some application domains, replay log should be reset as soon as the connection is closed. And in other application, it's okay to leave replay log as is. And it's a tricky problem. It's not that easy to solve. And what should be a default is also not clear. Let's see at existing solutions. And Project Reactor and Eric's Java team did a great job here, and they introduced such concepts as subjects, processors, connectable flowables, and domain-specific operators such as share, replay, ref count, connect, auto-connect, and so on to solve this particular problem. And this is actually a great place to start if you want to implement your own solution. But we cannot simply duplicate it or slightly adjust and adapt to Kotlin, because this API is Java-centric. It knows nothing about coroutines, about flows, about cancellations, and instead of suspensions, they have to manage a back pressure. But still, we carefully studied these implementations, their use cases, their trade-offs, and eventually ended up with our own solution. Welcome everyone, shared flow. Shared flow is just a flow that has a replay cache that can be read as an atomic snapshot. But again, as with state flow and as with Kotlin standard library, it comes into flavors: regular shared flow and mutable shared flow, which is a little bit more trickier. Mutable shared flow can be used to emit values from both suspending and non-suspending contexts. Its replay cache can be reset, and it also exposes its collector's count as flow. Why is it necessary, you may ask? It's for the sake of flexibility. For example, you can start collecting this flow and wait for subscription count to become 0, then wait for a few seconds, and only then terminate a source. Or you can do something completely different. It's up to you to decide. But this interface, implementing this interface is a tricky problem. So we're introducing a few convenience methods to work with shared flow. And like with state flow, we have a mutable shared flow factory to create a fresh instance of shared flow. And it can be completely customized. You can specify its replay log size, its buffer capacity, and what to do if buffer is full. For example, you can suspend, you can conflate values, you can throw an exception, or you can terminate the source. Whatever suits you. But what if you already have a flow and you want to share it, and you are not ready to rewrite your code for some kind of callback-based API with a fresh instance of mutable shared flow? For that, we have a share-in operator, which also can be customized. I'm not going to give you an example of how to use shared flow to solve a real-world problem here, to keep this talk short, but we have plenty of them in our documentation and coroutine guide, so please go and check it out. Apart from major updates, we also have a few small, but nevertheless important changes in flow, starting with core operators. Core operators are building blocks that can be used to express an arbitrary transformation over the flow. In fact, initially, we've carefully studied your feedback, your feature requests, your demands on various flow transformations, and was thinking what to do about it. Your use cases were perfectly valid. But if we were going to implement all of the proposed transformations, we would end up with like 100 flow operators. And it's not what we want to. 100 flow operators is hard to name, hard to learn, hard to maintain, hard to keep consistent and aligned with each other. So instead, we've decided to extract a set of low-level building blocks that you can easily combine to express a transformation you need. Then we introduced, and what's more important, enforced flow invariants, such as context preservation and exception transparency. And these invariants are crucial to keep implementation of flow operators safe and sound, and not able to interfere with other flow operators. It may sound a little bit vague, so let's jump right to the example and see how it works. Consider this terminal operator. It's pretty simple. It prints each element of the flow. Then, if an element is equal to 42, it throws an exception. Let's apply it to some flow, but not an arbitrary flow, but to a tricky one, this one. This flow emits a 42, then it catches an exception and emits 21. What are we going to expect here? First, please note that this flow implementation is actually incorrect. It violates exception transparency because the downstream, it signaled us that it has no longer interested in further values, but still we are trying to emit 21. Yeah, you may think it's kind of corner case and it's hard to write it manually, but no, it still is possible. It's still possible to do so by mistake, or because of some weird interaction of maybe helper functions. And it actually can break existing operators, such as first of null, and so on. And that's not what you want. If you're using flow in the initial release, 42 and 21 were printed to the console. And it's not that great. But in a newer Kotlin X coroutines, you'll get an exception. And this exception will be particularly detailed. It will tell you what went wrong, where it went wrong, why is it forbidden, and what's more important, how to fix it. And here it suggests us to use a catch operator. So let's apply this suggestion and see what happens. At the end, we'll have this: a simple, concise flow of single element with a declarative catch operator that handles an exception and a terminal operator. And that's it. Let's move on to the general coroutines updates, and starting with Android-specific ones. And here we have lovely additions for Android ecosystem, starting with optimized deck size of coroutines. And when I'm saying deck size of coroutines, I actually mean a deck size of application with Kotlin X coroutines. To be more precise on how did we measure it, how we measured it, we actually wrote a simple application with a few activities in it, and we used coroutines here and there: flows, channels, coroutine scopes, and regular coroutines, launchers, and asyncs. Then we built this application with array and minifier enabled. And so how much size Kotlin X coroutines package takes. We carefully studied our bytecode contributors, number of class file sizes, and trimmed down some debug metadata that is not necessary for Kotlin X coroutines to operate. And as a result, we've been able to achieve a major 30% improvement. As a side effect, startup time of applications with Kotlin X coroutines was significantly reduced. Most of the gains here came from the reduced number of class files, but also we've completely rewritten our service loader to be more array and disk friendly. So you can finally forget about any Kotlin X coroutines related stalls on your application startup. Last but not least, we've completely rewritten our coroutine scheduler that is used in dispatchers.default and dispatchers.io. As a result, we've been able to reduce the CPU consumption in various use cases by up to a factor of 4. If you're interested in how is it possible, please follow this link to pull request, which has internal documentation of coroutine scheduler. And here you can see all the implementation details, consider trade-offs, and benchmarks we were measuring. Let's move on to Java-specific updates. And let's start with run-interruptible function. Run-interruptible function is a bridge between a blocking interruptible Java world and non-blocking and cancelable Kotlin world. And it actually transforms any cancellations into thread interruptions and any thread interruptions into cancellations. But what's more important, it does so even for outer cancellations. For example, if this timeout coroutine was cancelled, or if the whole outer scope or your activity was cancelled, then it interrupts the current thread. Blocking QTake or any other blocking operation will throw an interruption exception, and this function will transform it to cancellation exception. So you can finally forget about your coroutines getting stuck in blocking Java calls as long as you're wrapping it in run-interruptible function. Apart from that, We also have an integration with Blockhound that helps you to detect blocking calls where they shouldn't have been performed in the first place, for example, in dispatches.default. And for advanced users and library authors, we also provide an integration layer with Java util concurrent flow from Java 9. That's it with Coroutines updates. But it would be unfair to leave you here without shedding some light on what to expect from the future versions of Kotlin X Coroutines. Our first priority is to stabilize shared flow and state flow. So please try it, use it, break it, and tell us about your experience, whether it's positive or not. And we're keen on evolving this API based on your feedback. Our second problem is resource management. If you have a resource that is closable and that you want to send over a channel that may be canceled both from receiving and sending side, and you want to close it exactly once, how to solve it? Currently, it's a tricky problem, but luckily we know how to fix it, and we're going to introduce a new API in 1.4 for this particular problem. We also heard your feedback regarding offer and pull methods on channels. And these methods, they're pretty useful to integrate with a third-party callback API, but they have major gotcha. Even though they claim to return Boolean or nullable type if false and null respectively if the channel is closed, they still can throw an exception, and it's easy to miss, even during a code review. So we're going to deprecate them and introduce a new methods on channel that have exception type reflected in method return types, leveraging inline classes and sealed classes. Flow API also have some room for improvement. And here we're going to provide a set of time-specific operators for UI programming, such as debounce, sample, throttle, and so on. Coroutine testing is not as pleasant experience as we would like to see it. So we're going to fix all the bugs, stabilize it, and maybe even make it a multi-platform dependency, so you can use it from common code, though it's still an open question. Finally, we're going to introduce a sliceable dispatchers. So we can take an existing dispatcher, let's say a dispatcher.default or an arbitrary thread executor, and you can make a slice to limit the concurrency of your application. But this slice, it will be piggybacking on existing threads. It won't create any new threads. So it will save you a number of threads and your application footprint and eventually battery life. That's it with coroutines. So thank you for your attention and have a nice Kotlin.